Okay, this is the second video on Chapter 18, Strength of Materials. In the first video, we had set up all of our variables for example problem 18-3, and now we need to start computing. So one of the pieces of information given to us in the problem statement said that the proportional limit of the steel is 34 KSI. So essentially what that means is we need to verify that we do not exceed that proportional limit. Otherwise, the equations become invalid. So rather than jumping directly to the load, we're going to calculate the Euler stress, F sub E. So using Euler's equation, F sub E is pi squared E over KL over R squared. So that's pi squared times E. E is 30,000 KSI. That's the modulus of elasticity of steel. So we've got pi squared times E divided by KL over R. Our K value is 0.8 because we have a fixed pinned column. So the design value we want to use is 8. And L, the length, is 12 feet. But you always need to check for consistent units. We can't have feet here and inches up here in KSI. It has to be inches and inches. So 12 feet is 144 inches. That's the unbraced length of our columns. That's KL over R, which was 1.17. So that's our KL over R. KL over R is referred to as the slenderness ratio. And we're going to talk more about slenderness ratio in just a few moments. Let's see, we've got KL over R squared. Okay, so we need to square this bottom term. So all we need to do is calculate this, and we should get that F sub E, the Euler stress, is equal to 30.5 KSI. So that's less than 34. So we're below the proportional limit, so the equation remains valid. Now the question asked not for the allowable stress or the Euler stress, but the Euler load, the critical load that will cause buckling to occur. So I could, suppose, go up here and use this equation, that PE is equal to, P sub E is equal to pi squared EI over L squared. But I don't have to do that. It's a little simpler than that. I know the stress that will cause buckling to occur, and stress is equal to load divided by area. Any kind of stress is load divided by area. That's kind of a fundamental principle of strength of materials. So if I want to know load, P is equal to F times A. So all I need to do is take this 30.5 KSI that I just calculated as the critical Euler stress, multiply it by the area of a 3-inch diameter standard weight steel pipe, which is 2.07 inches squared. And that gives me 63.1 kips. Kips was my unit of load I was using because I used a unit of stress of KSI. So looking at the PowerPoint I have on Blackboard, I can see that apparently from the last edition of the textbook to this one, the area of a 3-inch diameter standard weight steel pipe has changed in the appendix. So the answer here is slightly different than what's in the PowerPoint, but the process remains correct. So with a slightly smaller area value, we get a slightly smaller load, 63.1 kips. So as I said, for hundreds of years, this Euler formula, well, both of these formulas, for stress and for load, were considered to be correct. They were used, and that's how column design was done. But over the years, what we found is that the Euler formulas are pretty unreliable when we have a pretty low slenderness ratio. So I mentioned before that this KL over R, KL over R. So K, it's just a coefficient to do with the end conditions, multiplied by the unbraced length, divided by the least radius of gyration. This is what we call the slenderness ratio. And so if we have, for instance, a very long length and a relatively small radius of gyration, that means we're going to have a very tall, skinny, or slender column that is going to be prone to buckling. But if we have, so this would be a high KL over R. But if KL over R is small, if we have a relatively short column with a big, fat radius of gyration, and be shorter and more stout and less likely to buckle. So this is a KL over R low, a low KL over R. Well, if you take a bunch of experimental data and you plot the failure stress against KL over R, what we see is that if we just graph the Euler stress curve, it looks something like this. Okay, but the values, if we plot them as like a scatter plot, they follow the curve pretty well until a certain point where they just don't. Let me switch pen colors here. At low values, the line of best fit for this data diverges from the Euler curve. So, so what we need to do is we need to, when we're designing or analyzing columns, we need to account for this. We need a second equation to use in this zone when we have a low KL over R. So essentially, we're going to have two different equations. Okay, and so the AISC, the American Institute of Steel Construction, has developed the following formulas for steel column analysis. So it starts off with KL over R. We want to calculate the KL over R for our given column. And then we're going to compare it to the cutoff point, the value essentially right here, to figure out, are we in this situation, situation number 1, or situation number 2? Which of the two, well, I should point down here, not over here. So are we in this part of the curve? Maybe I can switch my pen color again. This part of the curve right here. That's not a good curve. You get the idea. Are we in this part, or are we in this part over here? So which of the two parts of the curve do we fall under? So the value we compare it to is 4.71 times the square root of E over F sub y. That's basically the cutoff point right here that divides the two areas. So this is 4.71 times the square root of E over F sub y. Now, for the most part, we're going to be using A992 steel, the steel that's used to make wide flange beams. So in that case, 4.71 times the square root of 30,000 KSI. 30,000 KSI is the modulus of elasticity for any grade of steel. And A992 steel, that's used for wide flange beams, has a yield stress of 50 KSI. So if we find that cutoff point, 4.71 times square root of 30,000 over 50, we get we get 115.4. So that's going to be a common value that we're going to be using, especially if we're dealing with a wide flange beam. If we're dealing with some other grade of steel that has different yield stress, we'll have to recalculate this value. But assuming we're dealing with wide flanges and it has a yield stress of 50 ksi, then this is the cutoff point, 115.4. So it all comes down to, is KL over R greater than 115.4, or is KL over R less than 115.4? And so if it's greater than 115.4, then we're in this part of the curve that follows the Euler prediction. And so, so the allowable stress, the load, the allowable load is 0.525 times the Euler stress times the area. So basically it's just stress times area gives us load, and then we multiply it by this factor of safety right here. So, so the allowable load is pretty much strictly based on the Euler stress. If it's less than 115.4, though, that means we're over here in this area, this part of the curve that doesn't follow the curve of the Euler equation, and so we have to modify it a little bit, kind of significantly, I guess you could say. So the P allowable in this case is going to be equal to 0.658 to the power of, and up in the exponent we have Fy over F sub E. So the yield stress divided by the Euler stress. Okay, let's put that all in brackets. Then we multiply that by the yield stress. Then we multiply that by the area. And then we divide the whole thing by 1.67. So as you can see, this equation it involves more computation. It's a little bit more complicated than this one. So usually students are kind of hoping that they get this one, that the KL over R is greater than 115.4. Because if it's less than 115.4, we need to use this more complicated equation. So in the next video, I'm going to do an example where we apply these AISC equations. But I think this is a good stopping point right here. And then the next video will just be the example problem.